Hello everybody and welcome back to ChemTalk, where today we'll be talking about spontaneity and Gibbs free energy. Now, this video actually includes two topics, and both of them are very closely linked to each other, and you're going to see in a little bit why and how. So the first question that everyone should be asking is, what does it mean for a reaction to be spontaneous, and how can a reaction be spontaneous? So a reaction that favors the formation of the products while releasing energy is a spontaneous reaction. So that means that the reaction is releasing energy and heat is a product rather than a reactant. So whenever the formation favors the products or the reaction is being driven forward, that is a spontaneous reaction. An unspontaneous reaction is the exact opposite. This means that the formation of the reactants is favored, energy is absorbed, there's a decrease in entropy, etc. So that means that heat is actually a reactant. This also means that the reaction is driven backwards, not forward. So an example of a spontaneous reaction is going to be fire. So as you go into it, a fire usually consumes a lot of reactants such as oxygen, and then it releases carbon dioxide. It also releases energy as heat. So because it releases energy, we know that heat or energy is actually a product of this reaction, which means that our reaction is being driven forward. So what is free energy? Free energy is the energy available when the reaction is being completed or when the work of the reaction is being completed. So like I've kind of mentioned this before, a spontaneous reaction releases free energy while an unspontaneous reaction absorbs energy. So like I have said before, this means that in an unspontaneous reaction, heat is going to be a reactant, while in a spontaneous reaction, heat is going to be a product. So whenever you see heat on one side or the other, that really just tells you whether or not it's spontaneous or unspontaneous. So when it's on the left side, it's going to be an unspontaneous reaction, and when it's on the right side, it's going to be a spontaneous reaction. Now the following equation is actually what we use in order to calculate Gibbs free energy. And just to state that this little degree sign that we see over here is a standard state, so that means that our temperatures and all of our heats of reactions are going to be at a standard state. They're also going to be all the same at constant pressure and constant temperature. So the Gibbs free energy equation is the change in enthalpy minus the temperature in Kelvin times the change in entropy. And usually you can get these values in the back of your textbook. You can also look them up online and get them off of a vetted website that usually ends in .org. Usually a lot of the times that you can find them in science magazines and stuff like that as well. So how is heat and free energy and spontaneity really related? So there's going to be a little bit of a quote-unquote cheat sheet that I have learned when using free energy and spontaneity. So in the following, we're going to have 5 categories. So the first category is going to be our change in enthalpy. So this is our heat of reaction. Our next one is going to be change in entropy. It's going to show us whether or not it's going from less reactants or less, and it's being divided into more things. So saying you're going from 1 molecule to 2 molecules or 2 molecule to 1 molecule. Then our overall expression of negative T delta S, that is also one of our categories. Our total Gibbs free energy is also one of our categories. And then the last category is going to say whether or not, according to these different conditions, is it spontaneous or is it non-spontaneous. In the first row, we're going to see that the heat of reaction is positive, the heat of entropy is negative. The overall expression of negative T delta S is positive, so that means that our Gibbs free energy is positive. That means that our reaction is non-spontaneous. That means that heat or energy is being absorbed into our reaction, which means that energy is actually a reactant in this reaction. The next column states that our heat reaction is going to be negative, our entropy is going to be positive, our overall negative T delta S is going to be negative, and that means that our Gibbs free energy is going to be negative. This means that our spontaneity of this reaction is going to be spontaneous. So that means that our energy slash heat is going to be on our product side, which means that this reaction is driven to go forward. When our heat of reaction is negative, our heat of entropy is also negative. Our overall negative T delta S is positive. Our Gibbs free energy can either be positive or negative. So when our temperature is low, that means that it's going to be spontaneous. This results in a negative Gibbs free energy. When we have a high temperature, this actually results in a positive Gibbs free energy, so that means our reaction is going to be non-spontaneous. In our last row, we're going to be able to see that our heat of formation is going to be positive, our entropy is going to be positive, our overall negative T delta S is going to be negative, and then if our temperature is low, it's going to end with a positive Gibbs free energy, so that means it's going to be non-spontaneous, and if our temperature is high, it's going to result in a negative Gibbs free energy, which means our reaction is going to be spontaneous. So overall, when our final energy or Gibbs free energy is positive or absorbed during the work, that means our reaction is non-spontaneous. And when energy is negative or when it is released during the work, our reaction is going to be spontaneous. It is going to be driven forward. Now let's look at a sort of example of the equation and how we use it in order to find whether or not a reaction is spontaneous or non-spontaneous. So right now we're looking at the melting of an ice cube. So what is the Gibbs free energy when an ice cube is melting at 20 degrees Celsius? So we're going to get our values from, I got my values personally from the back of my textbook. You can also find it in the back of your textbook. You can also ask your professor or your teacher if they have these values. And again, like I said before, you can also look online. So our temperature is going to be in Kelvin. So the temperature is going to be 273 plus 20, which is 293 Kelvin. My delta H is 6.01 kilojoules per mole, and my delta S is 0.022 kilojoules per mole. We're going to plug all this information into our delta G, and we want to make sure that our T and delta S are multiplied together before you do anything else with any of the other equations or variables or anything like that. We're going to follow PEMDAS when you're completing this equation. So our Gibbs free energy turns out to be negative 0.44 kilojoules per mole. This means that our reaction is spontaneous, which means that it favors the products. This also means that heat or energy is actually a product of our reaction. We want to make sure that we also kind of understand whether or not it makes sense in the real world or whether or not we're just kind of, getting the wrong numbers, and does it actually melt at 20 degrees Celsius, which is around to room temperature. So in real life, it is completely true that ice melts at 20 degrees Celsius, and that when you're having ice melt, you actually feel the cold release around you. So that is energy being released when our ice is melting. Now imagine the same ice cube is melting, but the temperature is negative 10 degrees Celsius. So we're using the same exact delta S and delta H values that I have in the previous equation, but all we're doing is that we are changing our value of temperature. Now again, I want to remind you guys that temperature and pressure is staying constant, so throughout this entire reaction, our temperature is staying at 263 Kelvin. Now after we complete our equation, we see that delta G is positive this time. It equals 0.224 kilojoules per mole. This means that our reaction is non-spontaneous. The products are not favored. It is our reactants that are favored. So this means that energy is actually a reactant. It is not a product. So this means that this reaction is non-spontaneous.